Ever wondered how databases handle large amounts of data efficiently? A secret weapon they often employ is dynamic hashing. Now you may be thinking, what on earth is dynamic hashing? Well, it's a technique that deals with changes in the size of the hash table. Imagine a hash table as a set of storage units or buckets that hold multiple key-value pairs. In dynamic hashing, we start with a small number of these buckets. But here's the trick. As we insert more elements into the hash table, the number of buckets can increase dynamically. This maintains a suitable load factor, which is the ratio of elements to buckets. By keeping this ratio balanced, we minimize the need for rehashing and improve performance. So to sum up, dynamic hashing allows for efficient handling of data, especially in large databases. Now let's dive into the components of dynamic hashing. At the heart of dynamic hashing are two essential components, the directory and the buckets. Their interaction is what sets dynamic hashing apart and gives it the ability to adapt to changing data loads. First, let's talk about the directory. This is a data structure that serves as a guide for where to find our data. Think of it like a map, with each entry pointing to a specific bucket in the hash table. Initially, this directory is quite small, pointing to just a handful of buckets. But as our data grows, so does our directory, expanding its pointers to accommodate new buckets. Now, onto the buckets. These are the actual storage units in our hash table, each one capable of holding multiple key-value pairs. At the start, each bucket is relatively small, conserving memory. But here's where the magic of dynamic hashing comes in. As we add more data and our buckets begin to fill up, dynamic hashing responds by splitting full buckets into two. This effectively increases our storage capacity without disrupting the rest of our data. The relationship between the directory and the buckets is a dance of give and take. When a bucket splits, the directory steps up, adjusting its pointers to accommodate the new bucket. And when data is removed and buckets become empty, the directory again responds, merging pointers where necessary to maintain efficiency. But what's truly remarkable is how this process minimizes the need for rehashing. In other hashing techniques, a change in the number of buckets often means having to rehash all the elements, a time-consuming and performance-hitting process. But with dynamic hashing, only the elements in the affected bucket need to be rehashed, significantly improving performance. These components, the directory and the buckets, form the backbone of dynamic hashing. Their combined function allows dynamic hashing to adapt to changing data loads, ensuring efficient use of memory and maintaining balanced load distribution. And that's what makes dynamic hashing such a powerful tool in data management. With the components in place, how does dynamic hashing work? Let's break it down with the three main operations: insertion, deletion, and search. First up, insertion. Imagine you have a key-value pair that you want to add to your hash table. The process begins with the application of the hash function to the key. This process generates an index which points to a directory entry. If the corresponding bucket has room for one more pair, then the key-value pair is stored there. It's as simple as that. But what if the bucket is already full? This is where dynamic hashing flexes its muscles. The bucket is split into two, creating more room. The directory is then updated to point to these new, less crowded buckets. This dynamic resizing helps maintain optimal load factors and keeps operations swift. Next, let's look at deletion. Say goodbye to a key-value pair. The hash function once again comes into play, determining the index of the directory entry corresponding to this key. The key-value pair is then removed from the bucket. But deletion in dynamic hashing isn't just about taking things out. If a bucket becomes empty after a deletion and its neighboring bucket is also empty, they can be merged into one. This ensures that space isn't wasted on empty buckets. The directory is updated accordingly, keeping everything neat and tidy. Finally, we have the search operation. To find a key in the hash table, we apply the hash function to the key, just like in the previous operations. The hash function provides the index of the directory entry, and then we search within the corresponding bucket for the key. Now you might be wondering, what if the key isn't there? Well, that's a possibility. But remember, hashing is designed to minimize collisions, and dynamic hashing goes a step further by maintaining a balanced load distribution. So while it's not impossible for a key to be absent, the chances are relatively low. These operations, insertion, deletion, and search, make dynamic hashing a flexible and efficient method for handling data. The dynamic resizing of the hash table based on the number of elements stored minimizes wasted space and improves memory utilization. Moreover, the ability to perform efficient insertions and deletions by splitting and merging buckets as needed without requiring rehashing of all elements is a significant advantage. And by dynamically adjusting the number of buckets, dynamic hashing ensures a balanced load distribution, minimizing collisions and improving search performance. But remember, with great power comes great responsibility. Dynamic hashing does require additional bookkeeping to maintain the directory and handle bucket splitting and merging, which can lead to increased complexity. And the directory itself can add memory overhead, especially for large hash tables with a large number of buckets. Still, these operations make dynamic hashing a flexible and efficient method for handling data, and that's what makes it so valuable in database systems and other applications where efficient indexing of large datasets is critical. Understanding the pros and cons of dynamic hashing is essential. So let's dive right into it. First up, the advantages. The most prominent benefit of dynamic hashing is its ability to adjust the size of the hash table dynamically. This means it can efficiently manage the space based on the number of elements stored. It minimizes wasted space, thereby enhancing memory utilization. Next, we have efficient insertion and deletion. Dynamic hashing sidesteps the need for rehashing all elements when a new key-value pair is inserted or an existing one is deleted. Instead, it simply splits or merges buckets as needed. This ability to adapt on the fly makes it a highly efficient choice for operations where frequent updates are the norm. And lastly, dynamic hashing ensures a balanced load distribution. By adjusting the number of buckets according to the load factor, it minimizes collisions and improves search performance. This adaptability means it can maintain optimal performance, even under heavy loads. But it's not all roses. Dynamic hashing comes with its share of disadvantages. For starters, it's a bit more complex than static hashing techniques. The need to maintain the directory and handle bucket splitting and merging adds a layer of complexity that might be off-putting for some. Additionally, there's the issue of memory overhead. The directory in dynamic hashing, while essential, does add a certain overhead, especially for large hash tables with a large number of buckets. This can sometimes make it a less desirable choice when memory efficiency is a top priority. So to wrap up, dynamic hashing presents a powerful tool in the world of data management. Its ability to adapt and maintain efficiency under varying loads is a significant advantage. However, its increased complexity and memory overhead are factors that need to be considered. Despite its drawbacks, the benefits of dynamic hashing often outweigh the cons, especially in large-scale applications. This adaptability makes it a popular choice for database systems looking to index large datasets efficiently. So, where do we use dynamic hashing in the real world? Let's dive into the practical applications of this intriguing technique. Dynamic hashing finds its most common use in the world of database systems. Now, imagine you're dealing with a colossal dataset, something so large it's akin to a digital ocean. You need to index this data efficiently to enable quick search, insertion, and deletion operations. This is where dynamic hashing comes to the rescue. In a database system, dynamic hashing helps in creating and managing indexes for large datasets. It's like a librarian who knows exactly where each book is located on the shelves. By using a dynamic hash table, the database system can quickly find the data associated with a particular key, making data retrieval a breeze. Furthermore, dynamic hashing is a great fit for databases because it can adapt on the fly. As the database grows or shrinks with new data entries or deletions, dynamic hashing adjusts the size of the hash table. This adaptability means that the database system can handle changing workloads and data distributions without needing to rehash or resize the hash table, which can be a time-consuming process. Think about it this way. Dynamic hashing allows the library to add or remove shelves as needed, ensuring that there's always just the right amount of space for the books. It's an efficient, adaptable system for managing data, but it's not just in databases where we see dynamic hashing at work. Other applications include file systems for efficient file storage and retrieval, distributed systems for data partitioning, and even in cache systems to ensure efficient use of cache memory. In conclusion, dynamic hashing is a powerful tool in the realm of databases and data management, enabling efficient and adaptable data handling. It's like having a super smart, adaptable librarian managing a vast library of data, always ensuring that you can find exactly what you need, exactly when you need it.